Have you ever wondered why your voice sounds different to you than it does when you hear it on a recording? And just a quick question, how many of us like what we sound like on a recording? Let's see, raise your hand. Lying. Yeah, not many of us. Most of us like what we sound in our head versus what we sound on a recording. If you record your voice on your cell phone or something like that, we don't like what that sounds like. Well, I want you to try something. I want you to say out loud the word girl. Girl, girl, girl. I know what that sounds like. Now I want you to take your hand. I can't use this hand. Take your hand, kind of do it like a little hole, like so. Put it up to your mouth like that, and then say it again. Girl, 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 girl. It sounds way different. Why does it sound different? What is my hand doing? Today we're going to explore that. We're going to explore wave properties such as interference. We're going to explore wave properties of destructive and constructive interference. We're going to talk about resonance, and we're going to talk about natural frequencies. All of that is going to get to why my voice sounds different when I do different things, and specifically why my voice sounds different in my head than it does when it's on my cell phone. The next question I have for you is, which one of those voices is correct? Is it correct what I think I sound like? Or is it correct when I hear my voice on a recording? Recording obviously maybe has some disruptive properties to it because of all the electronics that happen in a cell phone. Who knows? So we're going to discuss all of those features. Before we do that, we're going to take one small step back just so I know that you and I are all on the same page when we're talking about weight. Okay, so you've seen this animation before, but I've never really explained it. It was up to you to kind of look at it and understand what's going on. So up here we have a longitudinal wave. There are two examples of longitudinal waves that we want to talk about. The one that we will talk about most are sound waves. And I've been talking about sound waves the most because that is, most prevalent to our life here in the Northeast of New England. The other type of longitudinal waves that may or may not affect us are earthquake waves. There are two types of earthquake waves, and this talks about it. Primary waves, P waves, and secondary waves, S waves. Primary waves are waves that go back and forth, and those are the waves that are called the primary wave for an earthquake. Why is it called the primary wave? Maybe it's the first wave. I don't know. Look, there's a link right there that you can look at and read about. That's not our focus today. Our focus is what's going on in this little animation. Here you have it's like a bar, and that bar is oscillating at a constant frequency. Oscillating just means back and forth at the same frequency. And you can see in both pictures that there's this dark spot that seems to move all the way down the screen. And then there are these open spots that seem to move all the way down the screen. Those have specific names. The dark lines are called compression. And those compressions propagate or move all the way down the screen. The open spots are called rarefaction spots. R-A-R-E-F-A-C-T-I-O-N. Rarefaction, one word. And those also seem to move all the way down the screen. Now, just like a sound wave, those particles, if you notice, they highlight a red particle there. They put an arrow on these two. You can pick any particle in this whole thing. I can put the cursor right there under that group. And you will see that group, they just oscillate back and forth. They don't actually move because waves move energy. They do not move matter. So for a sound wave, the waves that I like to talk about, the air right in front of my mouth hits an air molecule, hits an air molecule, hits an air molecule, hits an air molecule until it gets to you. So the speakers where my sound is coming from, my voice is coming from on your computer, unless you're wearing earbuds, which would be just closer, the sound hits an air molecule to another one, to another one, to another one, to another one, until it gets to you. Otherwise, when we're in class, I drink coffee all the time. I'm a coffee fiend. You would smell my terrible coffee breath all the time if I'm in the front of the room, if the air right in front of my mouth made it all the way to you in your seat. That's not what happens. It's just a collision, it's excessive collision of air molecules until they get to you. That's also why when you yell, your voice loses energy as it goes down, right? I can yell, it's really loud up by me when I go, really loud up by me, but further away, it might not be as loud because as those air molecules collide, as any two objects collide, that collision takes energy. So there's a loss of energy with every air molecule collision. Now, sound travels in all three different mediums, in solids and liquids and gases, and sound travels the slowest in a gas because the molecules are so far away. That molecule over here hits a molecule over there, hits a molecule over there, and because they're so far away, that takes more time. So sound travels the slowest in air. Then in a liquid like water, sound travels a little bit faster. So like if you've ever been underwater and there's like somebody's watch beeping, like an alarm or something like that, it sounds like it's kind of loud, louder than in air. Well, that's just because their molecules are so close together, it's traveling faster, so it gets to you faster, losing less energy, so it sounds louder. In a solid, where the molecules are packed really, really, really dense, sound travels the fastest because it is just bump, 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 bump right next to each other. So when I hit the table as hard as I can, that energy propagates through, but like I said, it goes really fast. But the table molecules, the wood molecules, didn't go anywhere. They just vibrated just like this animation, back and forth. Now, every other kind of wave you can think of that's not a sound wave or a primary earthquake wave is a transverse wave. Now, these are the waves we picture most of the time because they're easier for us, but the same thing happens. If you notice, look at any group of molecules. Those molecules just oscillate up and down. Those molecules oscillate perpendicular to wave motion, as these molecules oscillate parallel to wave motion. Now, same idea applies. These waves transfer energy. They do not transfer matter. And then the last wave, and we don't really talk about these waves, but the same rules apply, are these surface waves. And you can see these surface waves seem to travel in a circle. These are like water waves. And that happens no matter where you are in the water. Obviously, the further down, the less interference there is. But they travel and they have this circular motion. But if you notice, the displacement of the wave particles are still zero. Again, because waves transfer only energy. Now, you might be thinking to yourself, but I've seen people surf, and water often brings in like trash and things onto shore. Well, surfers manipulate the surface of the wave such that they're riding that energy in. That's what they're doing. If they weren't coming on that angle, if they were just trying to go perpendicular to the wave, they wouldn't go anywhere. So if you notice when a surfer is surfing, they're going on an angle with the wave. So they are manipulating the wave so they can surf. The trash and things, any current or undertow, that also has an effect, and that is something totally different from the wave. That's a property of the ocean itself. So those are different things and different ideas that you may think, that you may hear, but what we need to know and understand is a wave transfers only energy. A wave cannot transfer matter. Now that we really have an idea and understand that, again, we're going to talk about wave interference. We're going to talk about constructive and destructive interference. We're going to talk about natural frequency and resonance. So the first thing we're going to talk about is wave interference and the principle of superposition. Now remember, waves are just energy. They're not physical things, which means I can get one wave traveling and another wave traveling to interfere with each other. Anyone that sings or plays an instrument in a band or a chorus, you know this is harmony. You want all of our waves to go and interfere with each other so the group sounds really good. Everything is louder, everything is in the same tone or the same frequency, and it sounds good. Now you're thinking, why the heck are you showing me, Mr. Rose, a picture of you playing baseball for the New York Mets and catching? Look, there's me catching for the New York Mets. Woo! Haha, no, that's not me. That is just my face superimposed on a Mets player's body with those awesome glasses. So we already knew what superposition was. A lot of us have played with superposition before when we put one object on top of the other. So here we physically cut out my head, put it on top of this picture, and now I have a superimposed image. So that is the law of superposition, and waves obey that law. So when I have two or more waves and they interact in such a way, I can make the crests, the top part of the wave, I can make the crests bigger to have bigger amplitudes. I can make the troughs bigger to have bigger amplitudes. And when those two things happen, we cause interference patterns. We cause constructive interference patterns, where the waves get bigger on the top and on the bottom. And we have destructive interference patterns, where the waves totally cancel out. And all of a sudden it would go from like a loud sound, and then it's going to bigger and bigger and bigger and bigger and bigger to a big sound, and then it's getting smaller and smaller. So those are two examples, and I'm going to show you what that looks like. Okay, so check this out. We have one wave and we have a second wave, and these are both transverse waves. Now remember, both transverse waves and longitudinal waves act in this fashion, but it's easier to demonstrate with transverse waves. So when these waves travel towards each other, and I can control that, you see I have one wave on top of another wave, and now when I have, there we go, this crest on top of this trough, what do we think happens? Well, this crest, the medium this is traveling through, can fall into this hole, into that trough. So the sum, when I put the sum together, that looks like, get rid of wave 1 and wave 2, it is canceling each other out, almost that flat line. And it's almost a flat line just because I didn't line them up perfectly. So when you see the waves on top of each other, and this is called 180 degrees out of phase, this is a total, there we go, a total cancellation of sound. And there are demonstrations I'm trying to figure out how you can set them up at home where you can see this, where you can physically hear dead spots in sound, because one wave is physically on top of the other wave and it cancels out. This is called destructive interference. Now, as the waves continue to propagate, going to get rid of that sum again, the waves keep moving just like nothing happened, because waves are just energy. So they superimpose on top of each other. And there we go. Now we have one wave directly on top of another wave. So they're superimposed on top of each other. That means instead of an amplitude that is that high, the amplitude will be twice as high because the waves are now building up. This is called constructive interference, where the waves construct and build. So this would be, if you were hearing it, something that is louder, a louder sound. The amplitude gets bigger in both the crest and the trough. Remember, amplitude is measured from the medium to the very bottom of the of the crest. Oh, that's a trough. The very bottom of the trough, or the very top of the crest. Now I'm going to rewind these guys, and I'm going to go to automatic. There we go. So now we can see it happen live as they go back and forth. All right, they're going to bounce and now come back. A crest on top of a trough. The white line is the sum. You see it cancels out and then gets bigger and smaller. And then the waves continue to propagate just like nothing happened. This is just super slow motion of waves. So you saw where it flattens out. As the two crests get on top of each other, the two troughs get on top of each other, gets bigger and bigger and bigger to show that constructive interference. Then you'll see the crest on top of the trough, destructive interference. And then it keeps going like nothing happened. They don't even care that they were interacting. Now that you know a little bit about wave interference, constructive and destructive interference, we're going to talk about standing waves.